Thank you for the nice introduction, and I would like also to thank you, the organizers, for giving me the opportunity to present our work in this nice NGSE postdoc series. In the talk of today, I would like to show how advanced modeling can help understanding the morphology formation for solution-processed solar cells. So, but already now I would like to point out, don't be afraid, there won't be any equations actually in the talk. I believe it's likely that you see some things you've never seen before, and so I hope you will enjoy the talk. So I will first introduce the context and objectives, then say a few words about the theoretical framework we use for simulating this morphology formation. And then we'll mainly focus on applications. The first one to perovskite, where we try to handle the question of the impact of the drying rate on perovskite formation. And then we'll switch to organic photovoltaics, and there we focused on the reproducing the formation of the bulk heterojunction for a P3HT PCBM system. Why P3HT PCBM? It's not the newest system, of course, but the main reason for this is that we have a huge amount of data on this system that we need to check our simulations. And then we'll finish with the outlook. So first of all, since we are initially not part of the PV community, it's highly probable that some of you do not know us. So I would like to take some time to present ourselves. So we belong to Professor Harting's group at the Helmholtz Institute for Renewable Energies. And the topic of this group is the dynamics of complex fluids and interfaces in general. We are a theory group, and our activities is that we develop and apply simulation techniques and analytical theory to understand the behavior of complex fluids. Complex fluids is, I would say, to summarize everything that is complicated. This can be turbulent flows, reactive flows, flows in porous medias, suspensions, nanoparticles, and of course, fluids where something's happening from the structure point of view, demixing, crystallization, and so on. As a theory group, our tools range from analytical theory to high-performance simulations. And so within this group of Professor Harting's, we are a small team which is working on solution-processed photovoltaics, with the objective to understand the origin of the film morphologies in these systems, so as to improve the processing methods or even propose new processing methods to improve the thin films. More precisely, well, you probably know that the understanding of the process-structure relationship in organic photovoltaics is still quite poor, and there are good reasons for this. The first one is that this is actually a very complicated coupled thermodynamic kinetic problem. And the second one is probably that experimental characterizations are very challenging. You might have nice pictures sometimes like this TM picture of a ternary or PV blend, or this SEM image of a perovskite film, but in general, you do not have all the information you would like to have. So as a consequence, the understanding mainly relies on trial and errors, and the knowledge is mainly experience-based. And on the other hand, the point is that for these systems, perovskite and organics, efficiency and lifetime still need to be improved. And we know that the morphology plays a role for this. And so, of course, we would like to understand how we can tune the morphology with the process so as to choose our morphology to fabricate the best possible solar cells. And our assumption is here that if we are able to calculate how the processing conditions impact the cell morphology, then we'll better understand and propose design rules for inks for processes that will rely on physical chemical understanding. The objective at the end is to find, of course, the best processing conditions to optimize the solar cell stability and efficiency. So now I would like to say a few words about the theoretical framework, but this will be a very general consideration on what we need to tackle this problem. So what we want to do actually is that we want to simulate the morphology formation of these photoactive layers, depending, of course, on the material properties, but also on the process parameters. And we want to characterize the morphology in terms of the number of phases, thermodynamic phases that are here, their type, their amount, also the domain sizes, the topology, the composition of the separated phases. If there are crystals, of course, the crystallinity, what kind of crystals do we have, the orientation, their size. The interface density is also important, and if, in particular, in the case of perovskite, the roughness and the substrate coverage you can get. Having a look at the literature of in organic and perovskite photovoltaics, it turns out that we need several physical processes to describe this film formation process. The first one is, of course, solvent evaporation, because the morphology formation is triggered mainly most of the time upon drying by concentration increase. What are these formation processes? This can be related to liquid-liquid phase separation in some cases, in particular for OPV, but also it can relate to crystallization. Moreover, interactions with the substrate are important, and mass transport may occur through diffusion, of course, but also advection of the species. A very crucial feature is also that all kinetic properties in such systems are very composition dependent. You can imagine that you start with a dilute solution where everything happens very fast. And at the end of the drying, you end up with a solid where everything is significantly slower, which results in the fact that at some point, the evolution of the morphology is kind of kinetically quenched. And if you are dealing with rough films, of course, you need the surface of the drying film to be free to deform, to generate pinholes and so on. So to handle such a problem, it turns out that the so-called phase field simulations are very well suited. To make it fast, this is a continuum mechanics approach, which means that unfortunately we do not have the molecular details, but we have large time scales and length scales potentially. This is what we gain. And one interesting feature of this approach is that all the interfaces we'll have in the systems are described as diffuse interfaces, not sharp interfaces, which makes it very easy to handle them, basically, from a numerical point of view. And with such simulations, what we do, basically, is to resolve the kinetic evolution of a system towards its thermodynamic equilibrium, knowing that in most of the cases, it would be quenched at some point in the evolution towards the equilibrium, but will never reach it. Phase field is an old method. It's a well-known method. It's a widely applied method for many different material systems. But when it comes to this particular problem, the literature becomes astonishingly scarce, actually. And here I want to summarize what are the most relevant contribution to the problem. The first one is the work of Olga Vodo's group in the last decade. They have investigated evaporation-induced liquid-liquid phase separation with application to organic photovoltaics. Here you see pictures from their work where you see the drying of a polymer small molecule film from the top to the bottom for different evaporation rates, increasing evaporation rate actually from the left to the right. But the crystallization is not here, and most of the OPV systems are crystalline. Of course, perovskite, this is a lot about crystallization. Then there's the work of Jasper Michels also in the last 10 years. Unfortunately, there are not a lot of papers. They worked on evaporation-induced liquid-liquid phase separation or on evaporation-induced liquid-liquid crystallization, but not both together. And actually, the only ones who coupled evaporation, liquid-liquid phase separation, and crystallization are Seiler and Kim. Unfortunately, these were still very simple models, and this was applied to drug release systems and not to photovoltaics. So acknowledging this, we decided to develop our own code, which would fulfill the requirements we listed to handle the problems we want to investigate. And now I wanted to show you some benchmarks of the three building blocks on very simple cases so that you can figure out how it looks like. So let's start with liquid-liquid demixing. Maybe you probably know that you can describe the mixing property with the Flory-Huggins theory. And if you couple that with the so-called Cahn-Hilliard equation, you can describe the kinetic evolution of a blend that is demixing. And here, what I want to show you is the demixing of a binary blend, which is highly miscible, unstable. You see the volume fraction fields of both material. At the beginning, it's all homogeneous. And if we let the unstable system evolve, at some point, it demixes spontaneously everywhere at the same time. And in this case, you end up usually with co-continuous morphologies or droplet-like morphologies. If the system is not unstable but metastable, there's another phase separation mechanism, namely nucleation and growth, where you see nucleating droplets that appear not at the same time in the system. And in general, you have this kind of droplet morphologies in that case. So these are textbook examples, nothing new here. Now let's turn to crystallization. And here again, in the simplest case, in the single material, here in the simulation you are going to see, you will see the order parameter on the left. Blue means amorphous, and you will see red appearing, which means crystalline. And on the right, you have a field which tracks the orientation of the single crystallites. There are thermal fluctuations in the systems, which allows the nuclei to appear, and then they grow, they impinge. And then you have grain coarsening at the boundaries. So from such simulations, we can extract the time-dependent crystallinity. And if you do this for here different model parameters, this is not really important. You end up with curves that you can nicely fit with the classical Johnson-Mill-Avrami model. Okay, this is another benchmark test, nothing really new here, but I just wanted to point out that we really model the 4 phases of the crystallization process. And to finish with this section on the model, I wanted to mention the evaporation model. Here, we developed an evaporation model which allows us to take into account both thermodynamics and kinetics contribution to the evaporation rate. This is important because basically the evaporation rate and therefore the evaporation time fixes the time that is available for the system to evolve. We checked our simulation versus experiment on a very simple model PS toluene system. The experiments have been performed by our colleagues from Christoph Brabeck's group at the Solar Factory of the Future. This is what you see on the right. You have the relative film height depending on time for different solvent volume fraction. And the continuous line are the experiments, and symbols are the simulations. And you have a really nice fit here. And actually, you have both contributions here. The thermodynamic one at the beginning, the first phase is a constant evaporation rate phase with fast evaporation. And then you have kinetic limitations. You have diffusion limited evaporation because you have a polymer skin forming at the top of the layer. Okay. So this is, once again, not really new, but what is new is to couple all these physical processes to make a simulation which is interesting for our forming photoactive layer. And let's see how we can apply this to the question of the drying rate for perovskite. So probably a lot of you in the audience know that this is a problem to obtain smooth perovskite film with full coverage in many situations. And you probably also know that fast evaporation is crucial. And we wanted to check if we can understand this with a quite simple model that we have developed. And here what we did is that we placed two growing crystals in a drying film, and we checked which kind of final morphologies we observed depending on the crystal density, this is the x-axis, and depending on the ratio of the evaporation rate to the growth rate of the crystals. And so the snapshots here show you what you kind of final morphologies you can get from very smooth, nice films, what you would like to have, to very rough films, and even films with pinholes at the bottom right. And you can notice that if you want smooth film, you'd better be in the upper half of the phase of this phase diagram, which means that basically you have to evaporate fast, which is what you see experimentally. And this is here not about chemistry or whatever. This is a simple geometric effect, which is probably more general than what's happening in perovskites. Let's go a step further. And now, instead of having crystals already formed in the film, we let the crystals nucleate on their own. So what you are going to see here is a cut of a drying film. You have the perovskite concentration on the left, the vapor is on top here. In the middle, you have the order parameters. So at the beginning, everything is amorphous, and the crystal orientations on the right. Let's evaporate slowly. What you see is that the crystals form early, they grow a lot, they are big, and at the end, you have a pinhole. Now, if you dry faster, and really, really fast, what happens is that the film, in that particular case, has time to dry before the crystals can form, and then they form in a dry film. So this is smooth, and they are much smaller. Okay, and now let's check versus experiments. So here again, the experiments have been performed by our colleagues of the Solar Factory of the Future. And here you have on top the simulation results, at the bottom SEM top views of perovskite films, from low evaporation rate on the left to high evaporation rate on the right, sorry, turn around. And so what you can see, what you probably know, is that the faster you dry, the smoother the films are, the smaller the crystallites, and the less pinholes you have. And this is nicely recovered in the simulation. So here we have a general confirmation that evaporating fast is important when you have fast nucleation and growth. Okay, so this is the first preliminary example of what you can do with our code. You can invest, and then further away, of course, you can investigate how the processing conditions, like not only evaporation rate, but initial film height, initial concentration, impacts the final morphology, for instance. Okay, let's now turn to organic photovoltaics and the question of the bulk heterojunction. So here we focused on P3HT PCBM and processed from dichlorobenzene because there are a lot of data on the system, and in particular we have different papers with in situ monitoring of the morphology formation during drying. And so we could compare with this data to validate our approach. But before showing you all this, I will show you how we can already before have an idea of what's going to happen, considering only the thermodynamic and kinetic properties. So first, using literature data, we can generate the phase diagrams of this system. So I do not know how familiar you are with ternary phase diagram, but basically this is the concentration space you see on this triangle. 100% P3HT is on the bottom right, DCB on the top, and PCBM on the bottom left. And when you are going to dry, you go from almost pure DCB to no DCB, so down in the phase diagram. So when you see this phase diagram, I'm going to tell you what you expect at the thermodynamic equilibrium. First, you expect a two-phase equilibrium in the region of these green tine lights between a crystallite P3HT phase with a solvent inside and a solvent phase, the blue one, with a little bit of PCBM but no P3HT. Then you would enter the gray region, which is a three-phase equilibrium where a crystalline or aggregated PCBM phase appear. And then upon drying, the solvent disappear, and at some point the solvent phase disappear, and you end up with a PCBM and the P3HT crystallites. So this is what you expect from the equilibrium. But as we said before, this is a coupled kinetic and thermodynamic problem, and this is not going to happen actually. Why? Because during drying, the processes may or may not have time to occur, and there's a competition between evaporation and, in this case, crystallization kinetics. So let's check what we could expect. So first, with independent simulations, we can characterize the crystallization kinetics of both solutes in a solution at fixed concentration. And if we do this for several concentrations, we can then extract the crystallization time, say, depending on the volume fraction of solute. And you can end up, for instance, with these curves for the donors or for P3HT and for the PCBM. Okay, crystallization is faster in a dilute solution because kinetics is faster up to a certain point where the thermodynamic driving force is not enough for crystallization and you reach the solubility limit at some point. Okay. Then let's characterize our drying kinetics. And here on the right, you have plotted the relative film height, depending on time, for different evaporation rate we chose for our investigations. And you see that the film is dry within 1 to 15 seconds. If I report these time scales in the graph on the left, this is the gray zone. And what you see right now is that P3HT will have time to crystallize, but PCBM, even if it wants to crystallize, it won't have time. Okay, so now with these hints in mind, we can turn to the simulations I wanted to show you, which are simulations of drying of the ternary mixture, followed by an annealing. The color code is slightly different as compared before. You will have on the left the volume fraction field, in the middle the order parameter field, and on the right, once again, the orientation of the crystallites. Blue means solvent, and you will see red, which is P3HT, and green, which is PCBM. For the order parameter, the blue, the order of the parameter of the solvent tracks the vapor phase. And for the P3HT and PCBM, this will be the crystallites. So let's see what's happening. The film dries, and at some point you have a morphology formation. And then the film is dry, and as I said, there's an annealing behind, and so you see also the annealing. So let's have a look maybe one more time, and then I will show you some snapshots that are important. Okay, so at the beginning, everything's homogeneous. At some point, maybe here you see that some P3HT crystallites appear. Here you see more significantly the P3HT crystallite that are in some mixed amorphous phase. Shortly after, you see pure acceptor phase appearing. This is liquid-liquid demixing. Here, the film is dry, and so the morphology is a three-phase morphology, actually, with P3HT crystallite, an amorphous mixed phase, and a pure acceptor phase. And if after that you make an annealing, you start to have PCBM crystallization or aggregation, and you have purification of the phases, and at the end, you obtain a fully, if you anneal too long, you obtain a fully crystalline system with big phases. Okay, On this slide, I want you to show that we can extract information from such simulations that we can directly compare with experimental results. Here on the left, you have a snapshot from a paper that has been published by Christoph Brabet's group on in situ monitoring of the morphology formation for P3HD PCBM. So you have a white light reflectometric curve to have the thickness. And here on the right, you have the simulation results, and this corresponds to the black curve here. Then you have, for instance, the crystallinity curve here in the simulation, the red curve, and this corresponds to this curve got from GWAX in the experiments. You also have in the experiments light scattering curves here. We can also calculate the scattered intensity, and this is the gray curve here on this graph. And maybe a last one here, also from GWAX, you have the crystal coherence length here. And here in the simulation, we can extract the typical crystal sizes. Okay, so gathering. So I reported here on the right the morphologies of these films at the end of the drying. This is the left column, and at the end of the annealing, this is the right column, the volume fraction on top, the crystallinity on the bottom. And if we gather all what we can compare from our simulations to what have been observed experimentally and published, actually, we have a very nice agreement in the morphology formation pathway first, that P3HD crystallizes first, that phase separation is due to crystallization, and that only after then might be a liquid-liquid phase separation, and that after the film is dry, and that only after that PCBM start to crystallize. We have a good agreement on the sizes also of all these phases. And we also have agreement on the general morphology of a P3HD PCBM blend, namely this three-phase morphology with crystalline P3HD, an amorphous mixed phase, and a pure acceptor phase. Okay, this was validation. And of course, now what we can do with this, we can play with the model to try to see how we can tune the morphology. So here I varied some parameters of the model to show you that we can have different outcomes already at the end of the drying. So once again, you see the volume fractions fields on top and the crystallinity on the bottom. And so the first simulations on the right, you see is an effect of the evaporation rate. And when you decrease the evaporation rate, what you see here is that you let more time for the system to crystallize, which at some point becomes not really cool because you have crystals aggregating at the top and which blocks the evaporation. But typically here, depending on what you want at the end, we can say what's the parameter, the processing window, typically. Then the next effect would be what would happen if PCBM would aggregate faster. The next one also, okay, if the system is not that miscible, if it's highly immiscible, how would it look like? Maybe like this. And on the other way around, if the system becomes fully miscible, then we have once again another morphology. Okay, this was at the end of the drying, and we can do the same at the end of the annealing. I don't want to go into further detail. So to conclude, what we have done in the past years is that we have developed this unified phase field framework to investigate the morphology formation of printed PV, which allows us to handle the most important physical processes altogether. We have done these first successful simulations of film formation for OPV and Perovskite that I've shown you right now upon drying. And I wanted to point out also that we can simulate diverse physics. We can easily switch on and off these different physical processes. We can tune the material and mixture properties, and we can also simulate several different processing steps. So not only drying, but also solvent vapor annealing or something like this, for instance. We have code improvement perspectives. Of course, we are still processes that are missing, in particular the substrate interactions. We plan to implement this. Maybe you notice that the growth of the crystal is isotropic at the moment, and of course this is not the case in most of the systems you investigate. And in particular for perovskite, of course, we would like to implement the chemical reactions. But for the moment, we are working a lot on extending the validation of our approach to other PV material systems and to identify process design rules for them. So of course, first we are working on more modern PV materials, namely at the moment PM6Y6, but also all small molecule systems. And we carry on our work on perovskites. Thereby, we perform extensive comparison with experiments to get input data, but also to check that our simulations make sense. And once this is ensured, we try to find design rules for inks and for processing conditions. And here we have a current focus on the scale-up of the surface of the solar cells and on getting nice performant thick active layers. And last but not least, you have seen these different morphologies. And of course, we would love to say, yes, this one is good. No, this one is bad. And for this reason, we would like to go from the simulated morphology to the prediction of the cell performance, in particular, the efficiency, of course. And with this, I thank you for your attention. And this is our small group here with Yacine Melon working on small molecule OPV, Martin Majewski on perovskite, and Maxime Sibert on polymer OPV. So if you are interested, don't hesitate to contact us, and I'm ready for answering your questions.